Okay, so good afternoon, everyone. Welcome to the Biostatistics, Epidemiology and Research Design seminar series. This BERD seminar series is sponsored by Penn State Clinical and Translational Science Institute. My name is Liao. I'm professor of public health science at the College of Medicine. I'm leading this BERD core with Professor Mosak Chow, who is professor of statistics at University Park. So Mosak and I, we coordinate and organize this seminar series. Please email us if you have any questions regarding the BERD seminars or BERD services. So the BERD seminar series features statisticians and methodologists from across the university to present the topics on fundamental research method and advanced analytical techniques. So as you can see here, we have 8 presentations lined up for the fall semester, focusing on essential research method and tools for clinical and translational science research. The spring seminar schedule will come out in early January next year. So if it's your first time to join our BERD seminar, as you can see here, this seminar is set up as a Zoom webinar. So you are muted except for panelists. This Zoom session is being recorded from the beginning. If you have any questions, you can use the Q&A box. We don't have the chat box, so Mosak and I will monitor the Q&A box to see if you have any questions. After the seminar, you will receive the slides recording link and a short survey to gather your feedback about our seminar. So now I'm pleased to introduce our seminar speaker today, Professor Duanping Liao from Department of Public Health Science. Dr. Liao is a professor and director of the Ph.D. program in the Division of Epidemiology. He is a well-known cardiovascular disease epidemiologist. His paper on the cardiometabolic risk factors and cognitive function decline has been cited for more than 1,100 times. Dr. Liao has extensive experience and expertise in the application of epidemiological approaches to investigate on the progression and etiology of chronic disease. He has served as the principal investigator on many federally funded research studies. He also has a very successful collaboration with the investigators at Penn State on clinical and translational science research. So today, Dr. Liao will use real-world examples to illustrate 2 critical concepts in observational studies, mediation and moderation. So Dr. Liao, please take it away.
Well, thank you, Dr. Kong, for the nice introduction. Let me find my slides and share. I think what you see here is with the notes. I need to change it.
I didn't see your notes.
You didn't see the notes? Okay, great.
How about Mosak, you?
Okay, that's fine. Okay, well, it's a great kind of pleasure to start this academic year's BERD seminar. So today I'm going to talk about 2 kind of very important concept and methodology in using the observational study data. There are mediations and moderations. So because this is a webinar, so I cannot hear you. But if you have questions, just send a kind of question to Dr. Kong, so she would be able to actually stop me and let me.
Yeah, you can type
answer
in question in the Q&A.
Yeah. So you are welcome to interrupt anytime through this mechanism. So because it's not talking about too much theories, but how we actually use these theories in our practice. Okay. So we are going to talk about moderation first. So moderation, if you read throughout the literature in different disciplines, it has different kind of names or terminologies. So most frequently used names for this actually very simple and important phenomenon is interaction, effect modification, or like moderation. So what is an effect modification or moderation? So it is a phenomenon that a factor that modifies the causal relationships between a predictor or risk factor or a treatment and the outcome of the study. So it can be also said that the magnitude of the effects of your primary exposure to the outcome differs depending on the levels of your third variable. That's your effect modifiers. So very often, age is a very powerful effect modifier for many risk factors and diseases associations. And we are in this pandemic for more than 2 years already. Now, everyone almost knows that the COVID vaccine itself is a effect modifier, which modifies the COVID and the severe COVID infection relationships. So individuals with the COVID vaccine, their risk when they get infected with COVID virus, then their outcome seems to be better in the published literature. So that's a traditional example of this effect modification, right? So then what's the difference between all these kind of terms? So actually interaction is often used when we try to describe the relationships in a more statistically consistent phenomenon with the effect modification, but we want to be a little bit more conservative without making the statement of this is the causal relationship that changes the primary exposure and outcome relationship. So it tends to be more statistically description of what you observed in your data. In contrast, the effect modification or effect modifier is often used to make a more strong statement of the causal relationships. But these relationships is actually significantly differ statistically between those with the effect modifier and those without the effect modifier. So as you can see here, they lean towards different spectrums of confidence in terms of make inference on the biological causal relationships. One is more leaning towards the statistical phenomenon. Another is trying to make a strong statement about the causal effects biologically exist. At any rate, such a phenomenon is totally different from the confounding. The effect modification itself should be a biological phenomenon. So this phenomenon actually implies some deep research is needed to identify the mechanisms that explain such differences in relationships. So we tend to think that effect modifier is a real or hypothesized relationships with strong biological plausibility. And it's not, if it is true, then it should not be just observed in one given data set. It should be consistent across different data sets of the same population, right? So the reason that nobody has reported it, because we are fortunate that you are the first one to identify such a relationship. So let me switch to the next slides. So in terms of how we identify this effect modification, it's actually quite straightforward. If you think about this example here, we have a total population of about 14,500 individuals. They are divided into two groups. One is without diabetes at baseline. That's a total of 12,866 individuals. And the individuals with type 2 diabetes at baseline, which is a minority, fortunately, which is only 1,636 individuals. But out of this total observation, after 9 years of follow-up, as you can see here, vast majority of those without diabetes at baseline remain to be not having a coronary heart diseases. And unfortunately, 743 of them developed coronary heart diseases. And you have some similar pattern here. So you can calculate the odds ratio from this 2x2 table. So you get an unadjusted odds ratio of almost 3 with a confidence interval which excluded 1. So at this stage, we kind of think that individuals with type 2 diabetes at baseline, their odds of developing coronary heart diseases is 3 times higher than those without diabetes. So it's implied that individuals with diabetes, with type 2 diabetes, have a significantly higher risk of developing coronary heart diseases. By the way, coronary heart diseases is still the leading cause of death in this country and in many other countries. So that's the main hypothesis that we tested, and we say that individuals with diabetes are at a greater risk. How greater? It's about 3 times higher, right? But you can stop here. You finish your main hypothesis testing. But maybe you want to ask whether this phenomenon is dependent on sex. So usually what we often do in the epidemiological studies is that we kind of try to understand the previous publications and to see if there are any kind of hint of indication of a potential effect modification. So as you all know that females before their menopause, their risk of coronary heart diseases is actually lower than men. So people believe that maybe the sex hormones might be kind of responsible for such a relationship or difference in relationships. So how do we test whether the sex is effect modification? So now it's the same population, but we break it down into 2 groups. Group 1 is female, and group 2 is male. So here in this study, you have 8,211 female, and you have 6,291 male. So same thing that you have individuals, either they have baseline type 2 diabetes or they don't have baseline diabetes. So when you break down these 2, you calculate calculated that the odds ratio among female is 4.27. The odds ratio in men is 2.45. So now you can see here that compare females with diabetes, with baseline type 2 diabetes to females without diabetes at baseline. The odds of developing coronary heart diseases in 9 years of follow-up is actually 4 times higher. But in men, individuals with baseline type 2 diabetes, their odds of developing coronary heart diseases compared to men without diabetes is 2.45. So obviously you see these two odds ratios, they are actually pulling far away from each other. So in that case, we kind of did some simple Breslow day test to see if these two odds ratios are similar or different from each other. So here you have this Breslow day test of homogeneity of the odds ratios, these two odds ratios at this p-value. So it indicates that these two odds ratios are significantly different from each other, right? So when you apply this statistics in this very simple 2x2 tables, what you get is that there is a statistically significant interaction between sex and diabetes in their relationship to the incidence of coronary heart diseases. And your p-value for such a claim of statistically significant interaction is the p-value is actually less than 0.01. So that's using a stratified analysis. Basically, is that you want to stratify by your potential effect modifiers. So in this case, we are trying to stratify by sex. And if we look at the exposure and outcome relationship in two different strata of the population. So now you can test whether those two odds ratios are significant. However, in epidemiological studies or in observational studies, you have many other confounding factors. So if you just presented what I presented in the previous 2 tables or 3 tables, usually you are not going to get it kind of accepted because there are many other factors that can confound or bias what you have obtained statistically. So what we are doing here in this publication is turn those 2x2 tables into a regression analysis. So we use either Poisson regression or a proportional hazard model, try to take into consideration of the time to the coronary heart diseases development and spontaneously control for other confounding factors, including age, race, education level, smoking status, physical activity, and the percent of kind of saturated fat intake in their total calorie. And we also adjust for some other biological risk factors, such as low density lipoprotein. So as you can see here in the first column, if you combine the entire cohort, you have about 10,150 individuals who do not have metabolic syndrome at baseline. Now we are moving from diabetes to metabolic syndrome as an exposure variable. And we have a little over 4,500 individuals who have metabolic syndrome at baseline. So after 9 years of follow-up, among individuals without metabolic syndrome, 522 of them developed coronary heart disease. So translate into 5.07% of an incident. Among those with metabolic syndrome at baseline, what you have here is 496 of them developed coronary heart diseases with the incidence of almost 11%. So if you take a ratio of these two, it's I think it's about 2, right? You can also use Poisson regression to calculate the incidence density. So that's what you get here. So basically, in 100,000, no, sorry, 10,000, in 10,000 person years, you're going to have 44 cases of stroke. So now it's the person time. So what you have is the incidence density. But for individuals without, that's for individuals without metabolic syndrome. For individuals with metabolic syndrome, the incidence density is actually 88.7. Again, a little over 2 times higher here. So you can use proportional hazard model to calculate hazard ratio and use those without metabolic syndrome at baseline as a reference. What you get is 2.05. So that if you think this as a relative risk, then individuals with metabolic syndrome overall in the entire cohort, after controlling for all these confounding factors, they still experience almost like 2 times higher the risk of developing coronary heart diseases. Now we model the gender and the metabolic syndrome together in a model as an interaction term. So what we calculate out here is the same table in the entire cohort, but now break down by woman and by men on the right. So if you look at the hazard ratio here, what you get here is 2.46 for women and 1.86 for men. Both hazard ratios are statistically significant itself. Both hazard ratios were adjusted for the same confounding factors I listed at the bottom of the table. So we can also test the interaction terms in this proportional hazard model. So the interaction term shows to be, if you look at the incidence, if you look at the incidence density model, the Poisson regression model, it's 0.02. If you look at the hazard ratio, the test for interaction term is 0.06. So that's focus on the outcome on coronary heart diseases. And we also have the data on mortality, all-cause mortality. All-cause mortality included cardiovascular mortality. So since coronary heart diseases is the leading cause of death in this country for adults, so vast majority of individuals in the all-cause mortality analysis are from the coronary heart diseases, then mixed with the second leading cause of death, which is cancer. So you add cancer and cardiovascular and the pulmonary cause of death together, that's what you get in this layout. You can still see that the odds ratio for female or hazard ratio for female is 1.57, but for men it's 1.22. But these two here, if you look at the last p-value is 0.62. So point estimates points to that women have slightly higher hazard ratio than men, but these two hazard ratios are not statistically significant at this p-value level. So this example basically shows that this phenomenon that potentially a discovery in terms of the disease's etiology or mechanism is very useful to analyze the observational study data. to summarize this, the effect modification ought to be based on some kind of biologically plausible processes. With that in mind, we are driven to actually use statistical methods from the very simple 2x2 table, use the Breslow day test for the homogeneity of odds ratios, to the regression analysis from logistic regression, Poisson regression to proportional hazard models. All these models are available to test for statistical effect modification. So all of us in the BERD program have actually extensive experience of using statistical models to resolve the observational study data issues. So when your career hits this type of opportunities, do not be hesitant to contact any of us to help you out to decide which model is the best to do this test. So that's why I kind of encourage the young investigators to think about the methods, think about the data you have, to see what you can add to the literature that is different from people has observed. In the previous example, we have known for many years that metabolic syndrome put people at higher risk. But when I started as the assistant professor, that has been done by others. So I have to think about something else. Maybe I can add to the literature. So that's what we come to the idea of analyze that metabolic syndrome with the effect modification by sex influence the development of coronary heart diseases. So that's encouraging. But we also have to keep in mind, most of the studies that we are dealing with, we are funded by NIH to do the main analysis or main hypothesis. So in the previous example, the main hypothesis is metabolic syndrome is associated with higher risk of coronary heart diseases development. But those has been taken by the PIs in the project. So as a junior faculty or as a PhD student, when I started participating in the ERIC study, those have been occupied. I have to think about something that I have a niche. But unfortunately, the study was funded to test the main hypothesis. So when you pick up a study and the sample size is limited, and when you stratify the sample into half and half, in this case by sex, and then your statistical power is obviously decreased. So don't get totally disappointed if you don't have the statistical power to get a 0.05 for the statistical testing of the interaction terms, because you at least have a hint that it might be there, but you just don't have enough power to actually show it to be statistically significant at p less than 0.05 level. That's why you see a lot of literature also that people kind of use the p-values like less than 0.06, less than 0.07 to put a statement and indicating, leaning towards a significant effect modification, and then go on to suggest the future studies need to kind of resolve these issues and try to get a test or replicate by many other studies to see if there is an effect modification. So that's basically a very simple kind of scientific principle. When there is an absence of evidence compared to what you do in the analysis of an underpowered effect modification, which is the evidence of absence. So these two concepts actually point to different things. What you did in your underpowered study, you don't have the evidence, but it doesn't mean that you have the evidence to support it does not exist, right? So that's the underpowered issue that you have to keep in mind. So that's why a p-value not less than 0.05 should not deter you from think deeper. So any questions on the moderation part? Otherwise, I would switch because I still have less than 30 minutes. So now the mediation is a totally different kind of ballgame. So if you think about interaction is the basketball, so now mediation is, although it's a study of causal relationships, but it's totally not a basketball. Then it becomes a football game. So that's good for Penn State, I guess. So mediation is actually asking the question of why. So what do I mean by why? It means that we want to study the role or the roles of the mediators or mediation variables. That is in the causal pathway between your exposure and your outcome. Right. So we are not just asking whether there is a relationship between exposure and outcome. We ask how this exposure leads to the outcome. So we want to hope to open the black box that connecting the exposure and the outcome. So it's really seeking the mechanisms from different perspectives than the moderation. So in less kind of philosophical terms, a mediation analysis is trying to determine if an exposure and outcome relationship can be partially or even completely explained by the mediation variables or the mediators. So basically you have a set of 4 variables. You have your primary exposure or predictor. You have your outcome, which is Y. Then you have your hypothesized mediator or mediators. Then you have your traditional confounders. So in any study, the confounder are something we want to control for. Effect modifier, like in previous example, we want to identify. Here, the 4th set of variable would be your mediators. So confounder, you want to control for the same way as you did previously in the effect modification. But here is how you handle the mediator. Previously is how you handle the effect modifier. So in that sense, there are some similarities. But the mediator have different kind of framework in terms of its action. So here's your traditional kind of thinking about mediator, right? You have your exposure or your predictor, which is associated with your outcome. And you have your confounding factors you want to control for. That's the C here. And then you have the mediator, which is the middle box here, which is the center of the universe under this mediation model. So what we are trying to do is to see that after we control for confounding factors, whether your predictor, your exposure, would cause the outcome to occur by means of its impact, the impact on the mediator. So it's the action that the predictor work on the mediator, and through the mediator change caused the outcome. So you have a very clear sequence of action in theory. If you can draw your causal relationships in such a box, then you started to thinking about mediation. You started to put yourself on the right track. Again, everyone contribute just a very small incremental amount of knowledge to a given causal relationships. So even your mediator is correctly hypothesized, correctly tested, you do not expect that single mediator would explain everything, completely explain that the predictor and outcome relationship is totally explained through your mediator. If that's the case, congratulations, you hit a jackpot. But most often, we are not hitting the jackpot. So there is still remaining relationship between your exposure and your outcome that cannot be explained by the mediators you analyzed. So there is still the remaining relationship. So that remaining relationship in this framework is called the direct effects. But I prefer to think it as a remaining effects that the mediator cannot explain. So traditionally, people have been trying to understand this mediator in a more kind of conceptual way, not totally quantitative way. So what I mean is that we start order analysis, control for the confounding factors, the same confounding factors. So we try to remove the confounding from order analysis to begin with. And we try to run a model that is going to show the relationship between X and Y without controlling for the mediator. So you obtain the regression coefficient from the predictor to the outcome, controlling for confounding factors. And you run your second model, which is the same as your first model, but differ by adding your mediator into the model. So what you get is a regression coefficient between X and Y after controlling for the additional mediators. Now what you can do is comparing these two models. Then the change in the regression coefficient from these two models is due to only one thing, the one thing that differ in these two models. That is the model with the mediator to be controlled for. So we want to see whether control for mediator would reduce the regression coefficient, or the magnitude of the regression coefficient would drop dramatically, right? So in that sense, it's almost try to think about the mediator as a super confounder. So you control for other confounders, now you control one super confounder to see if it actually changes it. So that's to answer the question, does change of the X to Y effects would be via this mediator? If it's via the mediator, then the change in the regression coefficient should be huge. That's kind of boring. Let's take a look at this example. So here is the framework of this mediation. So what we try to test here is that the visceral obesity, which is actually estimated by the visceral waist circumference, or waist circumference is more reflective of the visceral fat. So we hypothesize that the visceral fat or increased abdominal obesity or higher abdominal obesity is associated with the development of other metabolic syndrome components, So a metabolic syndrome has 5 components. One is increased waist circumference. The other 4 would be elevated blood pressure, elevated glucose levels, low good cholesterol level, that's HDL cholesterol, and high triglyceride levels. So if you score 3 out of these 5 components, you are classified as having metabolic syndrome. But here we compose this metabolic syndrome into 5 components and take out the waist circumference as a predictor, treating the other 4 components as the mediator. Then in each individual in this cohort can have 0 to 4 other components, right? Totally healthy individuals, they would not have any other 4 components. The less fortunate individual would have all 4 components. So now in this example, we use age, race, sex, and smoking as our confounding factors. So this is under the theory that all these components are the results of our lifestyle behavior. That's what we eat and of what we do not do, like physical activity. So we eat too much, we don't do any exercise, so that we cannot burn out all those nasty things that we eat in. So this overeating behavior and a lack of physical activity would start to accumulate fat in your fat cells, especially within your abdomen. So over time, our belly becomes bigger and bigger. Eventually, our system, we have a very good system that we will produce insulin to sustain our ever increased demand to digest all those intakes, those energies, and convert them into fat to deposit in our belly. But everything has a limit. So when our system of insulin secretion to compensate for our high demand, one day was started to weaken, and crash. When the insulin secretion cannot meet the demand, we started to develop other problems like elevated blood pressure, elevated glucose levels, and our HDL cholesterol become lower, and our triglycerides will be kind of circulating in our blood instead of going into our fat cells. So your triglycerides would increase. Then you started to have the clustering of all the other components, all due to overeating, visceral obesity. So in this example here, what we did is very simple. So we control for age, race, sex, and smoking. In a proportional hazard model, what you get here is the regression coefficient from the elevated waist circumference. I think it's a logistic regression model. So the odds ratio of this regression coefficient is 1.46, which is statistically significant. And we run second model, controlling for the same confounding factors. And we still have our elevated waist circumference in the model, but now we force a variable which counting how many other components that an individual has in the model. So as you can see here, the regression coefficient dropped from 0.3764 to 0.050. And this regression coefficient from waist circumference is no longer significant, which is 0.505. And the odds ratio of this model from the waist circumference is 1.5. So what you can see here in these two models, the regression coefficient from your primary exposure variable has been changed, decreased dramatically when you introduce your mediators into the model. So you can calculate the change of the regression coefficient, which is about 87%. So the regression coefficient differ by about 87%. But the only difference in these two models is additional adjustment of the mediators, right? So here you see the mediator plays its kind of game with these two in this model when it's included. So that's what people call traditional approach to show that there is a dramatic change in the regression coefficient after you adjust for your mediators. But here you notice that there is no statistical test to see if this two regression coefficient or the change of the regression coefficient is statistically significant. So previously we stopped here and published data and hint that there is a mediation effect. So that's what people called traditional model. Until like several years ago, maybe a couple of years before the pandemic, people started to develop the statistical models to actually accommodate or to translate previous diagram by putting the regression coefficient into the context of those models, right? In this kind of flowchart here, you can see that it's the same mediation model, but if there is a relationship between X and the mediator, you can actually run a regression analysis and you can calculate the regression coefficient to show the effects of exposure on the mediator. You can also calculate the regression coefficient between your mediator and your outcome. And you can also calculate the remaining effects. So you basically, that's the beta X to Y. So that's the remaining effects or direct effects. So basically, what you just did in this three regression coefficient, you decomposed the total relationship into three separate regression coefficients. So this X to Y would be called the remaining effects between X and the Y. And X to M would be the effects of your exposure variable on the mediator. And then beta M to Y would be the effects of your mediator on the outcome. So if you combine these two regression coefficients here, that's your mediation effects, or also called indirect effects. So that's the modern framework that we decompose the total regression coefficient into three components. So I think before the pandemic, we can only use SAS. We can only use R to do this decomposition of the total effects. And the SAS actually catch up, and they published a new procedure called causal MET, this causal mediation effects analysis model a couple of years ago, a little bit kind of before the pandemic. So this package actually enables us to analyze various framework of models, be it linear regression, be it logistic regression, proportional hazard model, or Poisson regression, etc. So what we have done here in this particular example of using the metabolic syndrome and its components. So it's the same framework here that we try to estimate what is the regression coefficient here, here, and the remaining here. So use the causal MET procedure. The most important outcome here, the table here would be the total effect, which is 1.47. I think it's the odds ratio here. And remember in the previous framework, the total effects in the traditional analysis, the odds ratio is 1.46. Remember, this is the total effect of the elevated waist circumference. So, not surprisingly, the odds ratio from this direct analysis from the causal MET procedure is 1.47 or 0.48, right? So with this confidence interval. And what we are looking for is the direct effect, which becomes 1.05. That's after you control for the mediator. In the previous slides, I just flipped to, I think, is 1.05 here in this model. So at these two estimates are identical, almost identical, in these two set of different approaches. Now, what we are most interested in is this indirect effects or the mediation effects. What you can see here, the exposure variable or the elevated waist circumference operating through those four metabolic syndrome components and inserted a odds ratio of 1.46. So this total effect is been decomposed into the mediation effects and the remaining direct effects, with each estimator have its confidence intervals. And they also give you the percentage of mediation effects. That is almost 90 here, 89. But it's kind of funny that the confidence interval, especially the upper bound, can exceed 100. It cannot be realistically be more than 100%, right? It's a confidence interval. So it stopped at 1. So that's a problem that SAS has not resolved, nor does R resolve it. So what people used to do is when the upper limit of the mediation effects confidence interval is more than 100, they truncated it to 100. But the p-value itself is valid. So be careful, don't look at the p-values here, because the p-value here is actually testing whether the odds ratio itself is 1. In this effect, but not for for the odds ratios of the direct effects and the indirect effects. So they only the parameters highlighted in yellow, like the confidence intervals, the point estimate, and the standard error are valid. And the p-value for the percentage of mediation effects is valid. So the p-value itself on the direct effects and the indirect effects should not be taken from here, but it's more kind of inferred from the confidence interval, right? So in this particular table, which is direct copy from previous table, what you have is after you decompose the total effects between waist circumference and coronary diseases development into the mediation effects through other metabolic syndrome components. The remaining effects has an odds ratio in the form of odds ratio is 1.05. In terms of the percentage of the total effects, it's about 5%. And the remaining effects or this odds ratio itself is not significant. It's 0.52. So this p-value is meant to make a statement about this confidence interval here, 0.89 to 0.12. So then the mediation effects has this p-value, have this like 89%. So that's a good illustration of a mediation model analyzed with the causal met procedure in SAS. But although the mediation analysis is very powerful and it's very can draw a lot of attention, then you use it correctly. So that's why you see in a lot of analysis, people started to thinking about, I'm going to run a mediation model. But mediation, a word of warning is that mediation model aimed to identify and quantify the mediators that are in the causal pathway. So here is the key, the causal pathway. So that's why I said in the beginning, if you can comfortably draw this diagram, know the direction of action, then you can use the mediation model comfortably. If the mediators occurred before your exposure, then it cannot be a mediator, right? Because mediator ought to be the results of the exposure, not the cause of the exposure. So that's very crucial. It's a consequence of exposure, and through this exposure and mediator effects, it causes the outcome. So without that in mind, you can easily, without that those flowchart in mind, you can easily get yourself into more troubles than you can handle down the road. So my advice to a lot of students in our program is that draw a diagram, convince yourself your arrow is correct in reality. So with that in mind, always think about the temporal relationships. But the model I just showed you of the metabolic syndrome is actually have a lot of limitations. All those 4 components of metabolic syndrome, as well as the predictor waist circumference elevation, are measured at baseline examination of the cohort. So in that data set that I used to show this example, we do not know with certainty that those 4 metabolic syndrome components are the direct results of elevated waist circumference, right? Because they are all measured in the baseline in the same time. But the model itself is still valid if I believe I have enough literature to suggest that these 4 components are the consequence of our lifestyle choice as well as our behavior. So that is kind of a debatable area, whether your arrow is true or not true. But at least in theory, I can find literatures to support my claim. But that's also indicate that with a bulletproof mediation model analysis, you would need to have measurement at least over 3 time frames. So you have to have multiple measures of your exposure, your mediator, and your outcome. You got to make sure that your outcome occurred after your exposure and after your mediator. Then that's the true kind of test or identification of significant mediators. Otherwise, it's only in the previous slides, I only provided a hint of potential effect multiplication, potential mediation. I think my time is up. Okay, let me stop here.
Thank you, Dr. Liao. So we do have a few questions in the Q&A. Are you able to see them?
Okay, let me change the mouse. The first question is it possible to test 3-way or even higher level of interaction? Yeah, the answer is yes. With the statistical testing, it's very easy to test 3-way or more way. In practice, 3-way or more than 3-way interaction is very difficult to explain. So statistically, we can test any way of multi-way of interaction. Practically, people are usually try to be careful not to get themselves into something that is totally difficult to explain. So can the confounders influence mediator? Yes, confounders should have an impact on the mediator because a confounder qualifies as a confounder. They have to be related to the exposure. They have to be related to the outcome. They cannot be in a pathway between the exposure to the outcome. So in the sense, in the mediation model, your confounding factors should have already influenced or associated with your exposure and your outcome. And because the mediator is in between your exposure and your outcome, so your confounder must have an influence on the mediator. That's why in all the models, when you analyze the mediator, you control for a set of common confounding factors in both models. One from Susan is, okay. So yeah, I think I can flip back to the slides. So this is the numbers they fill into the mediation model. Basically, they try to show you what is the regression coefficient or the odds ratio or hazard ratio. So any measure of, because the regression coefficient from other models can easily be translated into the ratio, the ratio measures. So when you do a mediation model, the focus is on these betas. Okay. Yeah, I think so, because we all begin with we are all, well, the question is about the fit and the fat hypothesis. So there has been a long debate. Do we have healthy obesity? So people are healthy and obese, but they don't develop diseases. Actually, the debate from the other camp is that that's actually not healthy, because everything has a limit, right? So if I'm kind of regular weight, I'm kind of fit, but I started to be lazy and don't do any exercise, and I start to eat, overeating. So that has to do with public health, right? Because vast majority of people are not athletes. They are not having all those muscles built up, but we build up fat much faster than our muscles in the general population. So it's eventually all the carbohydrate that we take in, all the fat we take in, if we don't use them, it got converted into triglycerides and stored in the fat cells. And most of our fat cells are actually inside of our abdomen. That's where our visceral fat comes from. And visceral fat just happen to be the most close. Visceral fat cells are the most close to our intestine, to our colons. So those are the places that can easily get all what we eat in to be absorbed into the cells. That's when we have the insulin. When our insulin system crashes, what you see is our insulin keep secretion and becomes higher, and our fat cells still cannot absorb all the glucose, because glucose cannot be stored. It has to be converted to be stored into fat. And then what we develop would be obesity. That's type 2 diabetes due to obesity. But we don't become type 2 diabetes in one day. And then what's happening is that insulin still think that our body do not have enough insulin. Our pancreas would create more and more insulin. But more and more insulin would cause the hypertension. It's a strong stimuli to cause the blood vessels to. So this metabolic syndrome underlined by the mechanism of insulin resistance actually is a current leading explanation of there's no real kind of harmless obesity. But it's just more kind of, it's early stage and you don't see the effect yet. I think that's all we have here.
We still have 2 more questions, I believe. Maybe.
Okay, so that p-value, actually that p-value, that's what I mean by that. That particular p-value is not actually useful. I think it's on this slide.
The last question is about, okay.
Yeah, so I think you're talking about this confidence interval of 0.89 and 1.2. But this p-value is not a test of this regression to be significant. This regression, this odds ratio is from the regression coefficient of here. So this regression coefficient is somewhat translated from this particular direct effect. So no, this one, 0.05. So this regression coefficient of 0.05, if you take a natural log or raise the power to 2 point something, what you get is the odds ratio here. Exponentiation of 0.05, you get this odds ratio. So to test whether this regression coefficient is significant, you get the p-value of 0.65, right? So the regression of the direct effects is 0.05. The exponentiation of this regression coefficient from this logistic regression model has an odds ratio of 1.05. And with this standard error, the confidence interval of the odds ratio is 0.89 to 1.2. The test statistics for the odds ratio B equals to 1 is here, 0.65, not this 0.001. Anything else?
Yeah, the last question is about the hypotheses on interactions. Is it more often to use data-driven approach to come up with hypotheses on interaction, or just from the background, the domain knowledge?
I think this is a very good question. I'm an epidemiologist, so I often doing all of my analysis and hypothesis driven, but less data driven. So I often actually generate my hypothesis through the literature, through some much wiser guy told me that you got to look at something that might be of importance in terms of effect modification, or even in terms of the mediation. So I tend to do it that way. And that way help me focus on the things that I try to test and find. And there are other people who are data driven, because nowadays with the data mining, you use the algorithms to identify the relationships, you identify the interactions, and when you find it and try to explain it, try to narrow it, and eventually generate a meaningful, significant interaction, and then try to find it. So depends on where you come from. For me, I'm more kind of hypothesis driven, but for some data scientists, they might be more kind of open to data driven. So there's no gold standard.
All right. Thank you, Dr. Liao, for taking the time presenting here. So you see, your presentation actually generated so much more discussion about this topic. So yeah, I would like to thank everybody for joining us and staying late. So our next seminar will be in 2 weeks from now. It's about randomization and sample size estimation. So we hope to see you again in 2 weeks. Okay, so I'm going to close our webinar. Thank you for joining us and have a great evening. Bye-bye.
Thank you, Liao.